Hey, so this will be a video solution for problem 1 of the third mock exam, which is over current carrying wires. So we'll get started here. For the context, we have a partial square conducting wire, even though we're only going to consider this length, the magnetic field contribution from this segment of the square wire, and its length L. So I'll just label that real quick. This length is L. Actually, all of these are L, but we don't care about the other two segments here. This wire carries a steady current I squared, and the distance 2D away is this long straight wire. Long straight wire means it's essentially infinitely long. So when we do refer to the formula sheet later, we're gonna know what type of wire to use. So it's not gonna be a short wire, right? It's going to be a long wire, which means R, the observation distance or the relative position vector, that its length is much shorter than the length of the wire, which is true here because we have a long wire. That's what that means. And it has I long flowing down, but sorry, up or down, but we don't know yet. Find the magnitude and direction of the magnetic field at the observation location P due to the square wire. So again, just going to focus on this segment. Now, it's finding magnitude is just applying or knowing which magnetic field formula to use. And we already kind of talked about it earlier, but we're obviously not going to use dipole formula, right? We're going to use the wire formula, or not the ring formula either. That will come in later, in the later part of this problem. But for now, it's a wire, and it's not the very long wire though. This is just the square wire. So we will use the general formula for just a straight segment of wire. Mu naught over 4 pi Li. So mu naught, and obviously this B, it's B wire, but we're gonna call it B square because it's um you know the context of the problem. So B square is equal to mu naught over 4 pi times Li over, I believe, R, and then R squared plus L over 2 squared, right? Just make sure we have the right formula. Li over R times R squared, blah blah blah. Okay, so L is the length of the wire. In this case, L is just L. So we're gonna just keep L as L. That sounds a little silly, but R is going to be the magnitude of the relative position vector. So our observation is here, and it's this far away from the wire. And that distance is, of course, going to be d. So R is just equal to d. So let's plug it in. B squared is equal to mu naught over 4 pi times L. And the current flowing through the wire is I squared, which is unknown quantity here, divided by R is equal to d, square root of d squared plus, and then I'm just going to simplify, L squared over 4. So this is going to be the magnitude, but we also have to figure out the direction. The direction is going to be given by the right-hand rule. So if we refer to this picture here, if you were to kind of just take the, let's see how we can do this. Boom. If you were to just use this right-hand rule, and you were to point your thumb in the direction of current, so if the current flows like this, your thumb points with the direction of the current, then you see that when your fingers curl towards our observation location, P, it's going to be pointing out of the page. So we know that B squared has to be pointing out of the page. So we can write it as positive z hat direction. And this part is, again, just applying the right-hand rule. Hopefully that makes sense. Definitely make sure we're comfortable with the right-hand rule. I'll probably use this picture later as well. For a given square wire, current I squared, determine the magnitude and direction of the current I long and infinite wire such that the net magnetic field at point P is 0. So we already know that B from the square comes out of the page, positive z, which means that the magnetic field from this long wire, in order to cancel it out, has to point in the equal but opposite direction. So it has to point negative z. So we know that I squared has to point, sorry, not I squared, but B squared has to point, not B squared, B from the long wire has to point in a negative z direction to cancel out. But we have to figure out what direction is the current flowing for that to actually happen. So if the current was flowing down, let's see, if the current was flowing down, then by the time your fingers wrap around to your observation location P, it's going to be pointing into the page, which is what we want. It's going to be pointing in the negative z hat direction. But if you were to first try pointing your fingers in the positive y direction, then you see that when you reach the observation location, your fingers are going to be pointing out of the page, which is not what we want. So here we will want our fingers to point down, negative y, so the current is flowing negative y. So B long points in the negative z, but I long flows down in the negative y direction. But we still have to find the magnitude of this magnetic field. Well, we know the magnitude has to be equal, remember equal but opposite to the square for it to cancel out. So B squared is equal to, well, the magnitudes are equal to B long, but what is B long equal to? B long from the wire is going to be mu naught over 4 pi times, now we can use the other wire formula, this one, 2I over R, 2I over R. So, and this is going to be I long. And we know R, the distance from our observation, is going to be, of course, D. So this is all equal to mu naught over 4 pi times 2I long over D. And this will be equal to the magnitude of B squared, which we found in the previous problem. So just get that down here. And we can just rearrange and solve for I long. So these constants cancel out. And after a little bit of algebra, we see that I long should be equal to Li squared times D over 2D root D squared plus L squared over 4. And it looks like these will cancel out. So the final answer can just be Li squared over 2 root D squared plus L squared over 4. Let me just check that answer on my end as well. Yep. So this will be our answer, but of course, also remember to include the direction of the conventional current, which is negative y over here. And this next problem is even trickier. So the long wire has now been replaced with a small ring of radius r, which is much less than d. We're going to see why this is important in a second here. So yeah, it's I ring. We have to find the magnitude and direction such that the net magnetic field at P is once again 0. So to do this, and I got a lot of questions in the double plus for this as well, why can I not use the B ring formula? Because that's probably, when you look in the formula sheet, the first thing your eyes go to is to use B ring. But B ring, notice how it says on axis where Z is much greater than R. On axis means that your circle, if your circle was in, let's just call this X, sorry, let's call this Y points up, X points to the right, and Z points out of the page. So in this case, the circle is in the YZ plane, right? I'm trying to draw like a circle. When viewed from the side, it looks like this, but yeah, it's like in the X, imagine it being in the YZ plane. So to use this formula, your observation location has to be perpendicular to your location. That's kind of weird. Normally your circle is going to be this on axis means it's on the perpendicular distance. I know it's kind of hard to explain just drawing it out. But if let's just say your circle is on the XY plane, it's flat. And so I'm kind of reorienting our axes here. But on axis means it's perpendicular. Your observation location is on some perpendicular axis to your circle. So the circle is in the XY plane, it's lying flat on whatever surface. The observation location has to be perpendicular to the center of the circle. That's when you can use the B-ring formula. Or your circle was oriented like this, and your observation location was out here to the center, perpendicular to the center of the circle. That would be when you use B-ring. In this case, the ring is on the same plane as these wires, so we cannot use B ring. But why is this part important? Well, it's because we know that a loop, any loop, it doesn't matter if it's a circle or if it's a square or a triangle or whatever, any closed loop will behave like a magnetic dipole when you're far away enough. So R is much less than D, which means we're far away. So this ring actually acts like a magnetic dipole, and the magnetic dipole moment, this U, or this mu symbol, can be determined by using your right-hand rule and figure out, okay, what is the um, magnetic dipole moment, the direction of it. So if you can imagine if your current were to go counterclockwise and you did your right-hand rule, then your thumb will point out of the page, so magnetic dipole moment would be out of the page, which means it would look like a magnet was inside, and facing us out of the page would be the North Pole because the magnetic dipole moment points south to north. Now, if your conventional current was flowing this way, uh, counterclockwise, then your thumb would be pointing out of the page. And sorry, what did I say? If we already talked about this. So wait, I forgot which one I said. Yeah, if it's going this way, counterclockwise, it points out of the page. If it went clockwise, then the magnetic dipole moment would be pointing into the page, so it looks like a bar magnet with its south pole facing us, right? So either way, whichever direction the current is flowing, the magnetic dipole moment is going to be pointing into or out of the page. So the dipole will be perpendicular to this observation location. So we're going to use the B dipole, not parallel, but perpendicular. So this formula here. So B dipole perpendicular, B dipole perpendicular is equal to mu naught over 4 pi times mu over r cubed, I believe. Mu over r cubed. So here we know that this magnitude has to be equal but opposite to our b squared. So again, gonna take this formula and drag it down. So this is all equal, and their magnitudes are equal. They're different direction, but their magnitudes are equal. So let's just find the magnitudes first. So from here, let's figure out what is mu. Well, mu is going to be I times the area, so I pi r squared. So we see that this simplifies, or not simplifies, but it gives us mu naught over 4 pi times I pi r squared, r being the radius of the circle, I r squared over r cubed, not to be confused with the radius of the circle. This r in the B dipole formula is your distance. So that's going to be, again, d over d cubed is equal to mu naught over 4 pi li squared times d root d squared plus l squared over 4. Okay, let's cancel out some constants. So we are looking for I, with I being the current flowing through the ring, so I ring. We see that I ring is equal to Li squared over pi r squared times d times the square root d squared plus L squared over 4, and we have d cubed in the numerator here. So let me check my answer here on my end, and we see that this, oh yeah, this d cancels out with the d cubed, so our simplified answer is just going to be Li squared times d squared over pi r squared radical. So d squared plus L squared over 4. So this is our magnitude of the current. So let's figure out, is it flowing up or sorry, clockwise or counterclockwise inside this loop. So again, with the right hand rule, we saw that, maybe I can reuse this picture. Where did I put it? Oh, here. So we already saw that the conventional current, or from the I square, the magnetic field points out of the page. So from the square, it's out of the page. So we need, for the ring, it has to point into the page. So now you have to imagine, there's a lot of visualizing in 3D. So the magnetic dipole is either going to be, the dipole moment is either going to be pointing into the page or out of the page. Let's just choose one and see if it's right. So finding the direction is a bit difficult because you have to visualize in 3D. So for the current, is it clockwise or counterclockwise? Well, let's just see, what if it was clockwise? If it was clockwise, then right-hand rule would tell you, if you were to kind of imagine, kind of hard to do with this like iPad here, but imagine you were pointing your thumb or your fingers clockwise with the conventional current, your thumb would be pointing into the page. So if it was pointing into the page, it would act like a magnetic dipole where the south pole was facing us, right? Yeah, I have to kind of think about that myself here because it's hard to draw. So if the magnetic dipole moment was pointing down into the page, then because dipole moment points from south to north, that means the north pole, sorry, the south pole will be facing us. And magnetic field for a dipole, we know it flows out of the North Pole and into the South Pole. So if it were to flow from the other side, the North Pole, it would be, and it's kind of impossible to draw on a 2D surface, but it looks like your fingers or your magnetic field lines will be coming out of P, which is not what we want. We want it to be going into P. So that's no good. And so we have to imagine, okay, what if we were to the other direction? The conventional current were to flow um, clockwise. No, we just did that. What if it were to flow counterclockwise? So if it were to flow counterclockwise, then the North Pole would be the one facing us. And the South Pole would be going, would be on the opposite direction, more into the page. So with that, you can imagine that there's a bar magnet here. Magnetic field lines are coming out of the page and going into the page. I can't draw that on an iPad. If you guys came to Plus sessions, then we would be able to more easily show you guys. But on an iPad, it's kind of hard to show. So yeah, the answer is going to be going counterclockwise here because in the end, we want the magnetic field to be pointing into the page. Yeah, that was a lot. It's hard to explain on an iPad. So yeah, I flows, or I should say I ring flows counterclockwise. Yeah, that was a lot. How might your answer change if the ring were rotated 90 degrees on its y-axis? Would it be possible for the ring to cancel out the magnetic field at point P? So remember, from I squared, from the square, the magnetic field points out of the page. So to cancel out, we need the magnetic field to be pointing um, into the page. But the ring is being rotated 90 degrees on its y-axis, so this axis. So imagine that this ring just looks like this when it's rotated 90 degrees. So when it's rotated like that, the magnetic field, using your right-hand rule, I use this picture again, the right-hand rule will tell you the magnetic field either points uh, positive x or negative x when you curl your finger in the direction of current. I know this is a little bit confusing because for this right-hand rule picture, it's talking about current being the end result, but that doesn't matter for us. Using the right-hand rule, we see that the magnetic field from the current in the wire is going to be pointing in the x direction on the x-axis. It will never be pointing in the negative z direction. So the answer for 4 is going to be no. the B field, the B ring, will always point along along the x axis. So positive x or negative x, depending on if it's clockwise or counterclockwise. But yeah, uh, this is going to be the worked out solution for problem 1. And it's a little hard to explain sometimes, so I apologize, just because it's hard to show the right-hand rule on a 2D surface. But hopefully you guys can get plenty of practice with the right-hand rule and everything else. So yeah, hopefully this video was helpful. I apologize if some of the explanations were kind of difficult because it is pretty hard to show the right-hand rule on a 2D surface, but hopefully you guys can get plenty of practice with right-hand rule and everything else on this test. Best of luck for the exam, and yeah, hopefully see you guys more in our plus sessions next week.